All right, my wonderful students, thanks for being patient. We're ready with a cool demonstration, and hopefully it'll work out, the Van de Graaff generator. But before we do that, I have an announcement concerning special study groups, and it behooves everyone to listen up carefully. I've sent out invitations to 25 students from the combination of both sections. In this morning class, Sarah Allen, Maria Boyd, Elizabeth Johnson. Okay. Maria, are you here? Sarah, are you here? Okay. Joshua Speaker, are you here? Okay. Courtney Thornberry, you're usually here, right? Where are you? She's not here. And Juliet Verley. Juliet, are you here? Okay, good. All right, now they've been invited, so you guys check your web courses inbox. You'll see the invitation if you haven't already seen it, and we could talk about it after class. And there's a whole bunch more from Section 2. Danielle Adogi, Mivosh Albersky, Javier Alvarenga, Tatiana Amadeo Floret, Tanner Anderson, David Andrews, Christiana Champnella, Carolyn Cook, Joseph Dunleavy, Bria Fitz, Brian Hutchinson, Colton McFarlane, Tyler Momini, Natalie Olenek, Jacob Paul, Camille Robinson, Ashley Von Schuckman, Sean Tiernan, and Isabella Yerby. Now, those guys, a set of these people will be special study group leaders. For the rest of you, you'll be signing up to join one of their special study groups and have a 1-hour study session to get ready for exam 3, which is next Tuesday, a week from today. All right, and we'll be running these Friday afternoon until Monday night, and you'll have sign-ups sometime Thursday night when we get all the schedules set up and stuff. The schedule page is going to look like the following. This is the schedule page from last semester, and the one this semester will look something similar to it. Let's do a close-up of it. Up at the top, I'll put some kind of a distinctive image for you to key on visually so you know you're on the right place. Because this is where you're going to look at the schedule page, and then as soon as sign-ups become available, you'll click into the sign-ups page from this page. In other words, right down here below the red stapler, it says sign-ups link will be here. Okay, right in that red box. All right. And so when you want to sign up, and you're going to have to move really fast on Thursday night, so if I open it up Thursday night at 8 o'clock, all the spots might be taken by 8:05. So you really got to hustle. All right. And so that's why, I always make a distinctive image on the schedule page so you know where you are. Now, below there, you'll see the who, what, when, and where type information, plus mugshots for each of the SSG leaders. Here's some of the mugshots from last semester. And you'll look at it, and until the sign-ups are activated, you won't be able to sign up. But you will be able to look through all through the schedule and say, oh, okay, I want to go to either Danielle's or maybe Mivosh. Because he's going to be going on Monday night, and I have a lot of time on Monday night, right? Or whatever your schedule, whatever seems good to your schedule. Now, you guys that are going to be special study group leaders, if you elect to become a leader, you don't have to. But if you do, what you want to do is map out a time and a location. Like even reserve a study room in the library. For your study group. A lot of people do that. Or, like a study room over in Hercules somewhere, or over in the towers, or some people meet at Chick-fil-A. Or the tables outside Chick-fil-A. Any place on campus is set time, and you want to be able to tell the students. You can't read the fine print here, but it'll always have a mugshot of you and how they'll recognize you. So, for instance, Lauren Baker here, it says, you won't be able to read this, but this is what it says. How you will recognize me: pale blue T-shirt, jeans, and white Converse. So she's wearing her white Converse high tops. And then Nicholas Schaffer. I am a giant guy with a black security hat on. Okay, and so forth. So you guys will all be typing that in, and then I'll put it on the schedule page, and everybody will sign up. And then we'll do it again during finals week, or actually after the last lecture, and then between the last lecture and the exam for section 2, because they come first. So we got to get from the last lecture on Thursday, and I think it's till the next Thursday or the next Wednesday, we have to get all our SSGs in, and that'll be good. Okay? Question here in the front? You can only, the question was, can we sign up for more than one? And the answer to that is no. You can only sign up for one. And if you sign up for one and you don't go, we'll be taking attendance. If you don't go, you don't get bonus points. If you do go and take part in everything, sign the attendance sheet, you get 4 bonus points. And hopefully you get and even without those bonus points, hopefully you get, several points higher on the exams. I mean, that's what it's supposed to do. But you can only sign up for one. And if you sign up and don't go, you're on my bad list. The S list that starts with the letter S. Because I don't like it, because if you take a spot, somebody else that's really working their off to get a decent grade, a C, and they can't go, and you took a spot that they could have taken, but you didn't go, and they could have, but they're not going to get bonus points, and you're not going to get bonus points, so it's a big disaster. So you got, and that's why I emphasize the schedule page, so that you can see the schedule and figure out absolutely, positively that you can make it or not. And if you can't make it absolutely, positively, don't sign up for it, because then you'll be on my what list, and you don't want to be on that, because at the end of the semester, when I'm looking at grades, and I know you blooped up special study groups, well, you don't want that. Let's just put it that way. Okay, question in the back. Yeah.
I have 2 questions. One, will the final be over everything we've covered, or is it over just the last little bit?
The final is cumulative. The question was, will the final be over everything that we covered, or just the last little bit of the semester? The answer is it'll be everything from the beginning of the semester in January up until the last lecture in April. So. And the second question?
You said you get 4 points for going extra. Is it for this session and for the...
Yeah, the question was, do you get 4 points for each session? The answer to that is yes. So if you sign up and you attend and you participate and you sign the attendance sheet and everything like that, and then if your special study group leader turns it in to me the way they're supposed to, then you'll get 4 bonus points for this round, for exam 3, and then you can sign up for a completely different SSG leader session going into the final. Nobody's, you're not signing up to study with this person and only this person. You can switch to a different person, and you'll get another 4 points for that. So a total of 8. It's a nice chunk of change. I mean, if you think about it, bonus points. And for those of you that have gotten bonus points already from early iClicker registration, I can't believe it. I gave 5 bonus points for that. I'm gonna have to really give you guys some hard questions on the final to make up for all those. I'm just kidding. I won't. I'll just make a regular final. But if you get, you guys are going to have a lot of bonus points, so that's good. You know, if you earn them, you get them. Anyway, so that's kind of the situation. Any other questions about special study groups? The question was, will the points go to the final? The answer to that is no. They sit in kind of a special bin, but I use this analogy every semester. It's kind of like a peanut butter and jelly sandwich. You know, the bread sits in a separate package, and then the peanut butter in a separate jar, and the jelly is in a separate jar. But then you put them together, and you eat them, and then they get all smushed around in your stomach. And it's the same thing with bonus points. They sit there and until the end of the semester, and then we put them all together into a sandwich known as your semester grade. But you know, they're there. They don't. The SSG points don't go away. But they don't attach to exam 3, for instance, because we may end up dropping your exam 3. Okay, if that's the lowest of your 3 midterms. So we don't want and if we drop exam 3, that's good, but we don't want to drop those SSG points. Okay, so that's why I just say, just keep them in their own little bin until the end of the semester. Then make your peanut butter jelly sandwich. You know, eat your sandwich and it all gets smushed around and stuff. It's all going to be in there. All right. Another question in the back. You go to this page, this schedule page. You know, the one that is going to have some kind of a image at the top. It won't be the red stapler this semester. It'll be something else. You know, like maybe a picture of Bart Simpson. You know, something distinctive. And then right below that will be the link. See this right down here? It says sign-ups link. It'll be right there. Yeah, it'll be in web. This is in web courses. And so everybody will have an equal chance. So I'm hoping to have it activate Thursday night, you know, like 8 o'clock maybe. So everybody has a chance to get home, eat some supper and work out, and then go and, sign up and stuff. And join your group. Is that a good answer? Sound sufficient? Okay. Another question. Okay, let's keep going. I have a special kind of question. Take out your iClicker, and this one is going to be short answer. Okay. You're going to make a sentence today. This is a little bit different from questions that we've used before. You're going to start having sentence formation tasks in class and also on exams. Now today we're just going to do a practice sentence. You're going to make a Chuck Norris fact. And so make it a good one. And so what you do is, I want you to be creative, because we're just messing around with Chuck Norris facts. Well, eventually we're going to be doing science questions. Use this code table and form a Chuck Norris fact. So for instance, the sequence YIVU, and then you hit the send key, that stands for sharks are my friends. So this table of symbols A through Z, type in a set of letters. And go ahead and write it down in your notes if you want. And we'll be able to look at some of the answers. But you have to hit the send key when you've got your sentence put together. Good. I see guys looking at the screen very carefully. And I hear clicking. It's good. All right. Now we're going to be doing this from time to time. And we're going to also be doing it. Ooh. Ooh. CADJ. Chuck Norris, always. Roundhouse kicks Justin Bieber. That's definitely a fact. Actually, probably not a fact because he wouldn't want to beat up on somebody as weenie-ish as Justin Bieber. But yeah, unless if Justin Bieber it turns out to be a crook. Anyway. All right, 30 seconds. And it's all right to screw around with this. And a sentence is two symbols or more. Okay, so just typing in the letter N is not sufficient. A, B, C, D. That's not a very good sentence. That's not a Chuck Norris. And you're all going to be getting points for this, so because we're just practicing with it. But when we ask science questions, I'll be grading them. So typing in A, B, C, D will work, but it won't. It doesn't really make a true sentence. All right, 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. All right, okay, students. Let's see. AMD. Go ahead and switch to this display so students can see. This is what I'm looking at up here on the monitor. Go down and see if you can bring it down. See, there's only, see how there's one person? We're trying to move this. See how this? Every answer on this list there's only one person that sent that. And so, there's one, CADY. There's one that somebody typed in. Three people typed it. What is CADY? Chuck Norris, always roundhouse kicks, sharks. Yes, obviously that is true. Ooh, CADZ. Chuck Norris, always roundhouse kicks, French fries. Okay, CADV.
CADR goes retail.
CADR? What's that? Chuck Norris, always roundhouse kicks, slackers. All right, good. Ooh, what's CADSR? Chuck Norris, always roundhouse kicks, afraid slackers. Good. Anyways, so you can switch back to the regular. So what we're going to be doing with this, you guys, we're going to start tomorrow. We're going to have a sentence formation code table for deluxe science questions. And the thing I like about this kind of a question, you'll have one on exam 3 as well. What I like about it especially is you're generating the answer. It's you being creative in that you create the sentence, and then I see if it's correct or not. Now, if you think about it, multiple choice, I'm in control of everything with that. I write the multiple choice question, A, B, C. I even write the wrong answers. So you can't even choose whatever you can't make anything up. True, false, same thing. Calculation, you got to have the right number, and I'm the one that controls that. But on this, with this, you have creativity, and you know what? I read even in a big class like this, I'll put together I'll look at your code, I'll turn it into a sentence of words, and then I'll read it. And I'll say, yeah, okay. Just like I did, verbally in front of you. Chuck Norris always roundhouse kicks slackers. And so that's kind of a funny example, but it's definitely a Chuck Norris fact. And so that would get 1 point or 3 points or whatever the point value I assign to it. All right. So, and it will allow you to convey a little bit of complexity of thought in your, as you create your own statement. And as many students as are in here, 100 and something students, we could actually have 100 and something correct answers. And if we do, then you'll get the point. Every person will get the points. So I love these kind of questions. All right. Now, we're going to do a demonstration now of the Van de Graaff generator. But before we do that, I want to just point out to you and to anyone listening to this YouTube that's not in class, there is a YouTube of the Van de Graaff generator demonstration from a couple semesters ago. Here it is. This guy, kind of with that grin on his face. You gotta look at it in YouTube. It's in the demonstrations playlist. There's the actual address. But we're going to do some clicker questions after the demonstration, so don't put your clicker away. But let me pause the podcast, turn the lights all the way up, please. And now, what is your name again? Frankie? Frankie, come on up and we'll get you going on the Van de Graaff generator. Okay. All right. So you can view, as I mentioned, the YouTube video of it from a couple semesters ago. Now I have some clicker questions for you. And what I want you to do now is hit the refresh key because we got some multiple choice questions coming up. Okay. You always have to switch, hit the refresh key between multiple choice and short answer, or multiple choice and numeric input. All right, now and go ahead and add this to your notes. The metal sphere of the Van de Graaff generator is positively charged. Okay, go ahead and make yourself a sketch like you see there. Okay, it's kind of a stylized view of it. But you can kind of see it up here. And basically what it's doing is the humming sound that you saw, that motor, it's driving a belt. It's basically friction. And it's set up so that the friction, the metal sphere, it's kind of gold colored, that Frankie and Caroline were touching is positively charged. Okay, so make a note of that. And I'll probably be asking you about this on the exam, so make sure you think carefully. And what is the meaning of that? Positively charged. Go ahead and make a decision. That is interesting.
Yeah.
Could you feel it in your arms? I mean, like you don't really have a lot of.
No, I have fuzzy arms, but
Yeah, because when I turned it on,
I could feel
yeah,
it.
when I shook my
Did you-
hand, then I could feel it.
Did you guys see that the MythBusters video I put on our homepage? Yeah, they did one of they built their own,
Oh, cool.
and the girl, one of the assistants,
Yeah.
she was like 10 feet away, and she said, "Man, I could feel it in my arms."
Wow.
So that's pretty powerful. It's a lot of volts. All right, 10 seconds to vote. 10, 9, 8, 7, 6, 5, 4, 3, 2. Come on. Chuck Norris is going to kick you for being a slacker if you don't click.
don't get roundhouse.
1, 0. Roundhouse kicks. All right, now go ahead and show them this. Let's talk about this. We've got a spread in the answers here, and to me, there's no majority. Option B, go ahead and switch back now, please. Thank you. Option B is the correct one, and this is something that you can always be sure of, unless you're in like some kind of a lab where you've got a special source of alpha rays or some kind of atom smasher. We're using protons. Most of the time, the things that get rearranged are the electrons. So if something is positive, if something is positive, it's got absent electrons. Right? Electrons have been stripped away and shift off to Staten Island or something. All right, whatever, So now, a side note, Frankie and Caroline, their hair was also positively charged. It went flying out into the universe because all the separate strands of hair were positive. Each strand was accumulated, because those little, what happens is it's as if the positive charges are motating outward into their hair. Now, so it's not protons moving. What's really happening is that the electrons are being drawn from Caroline and Frankie into that positively charged sphere, because that's where the electrons want to go. All right, so they've been stripped away from it, and the motor keeps running, and it strips more and more of them away. That spark that you heard and felt is electrons moving from point A to point B. Now, moving from point A to point B, I want to ask you a hypothetical question here. Here's your next clicker question, multiple choice. Think of a red, positively charged piece of styrofoam or something, all right? And it's initially at rest, somewhere near like an inch away from the metal sphere. Which of these paths will it tend to move in? And go ahead and make a sketch of the paths and add those two vocabulary terms to your notes. Radially inward, that's path A. It's going in as if it's going on a radius of the sphere. And path B is radially outward. That's as if it's going outward along a radius of, in the same direction that a radius would be going for that particular sphere. And I was pretty careful about arranging those two lines, A and B, so they're definitely radial. Okay, so go ahead and vote. Okay, see you, Derek. 15 seconds to vote. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. Good. And it looks like you guys did a good job. Yeah, radially outward. Radially outward. If you have some little positive charge there, yeah, that's what's going to happen. And now go ahead and make a sketch of a negatively charged metal sphere. We could make one of these if we wanted to. Load it up with extra electrons, this one, net negative charge. And they tend to accumulate on the surface because they want to get as far away from each other as they can. So they go to the surface, and then once they're on the surface, they kind of distribute themselves so that they're as far as possible as they can be from the nearest excess electron. All right, so they're going to tend to be. Now, a negatively charged metal sphere is going to tend to attract that red piece of styrofoam, right? It's going to go towards it, all right? Now, this introduces for us the concept of a field line. Electric field lines are defined as the directions in which a hypothetical positive charge, aka the test charge, would tend to go if it starts from rest. Okay? And if it's in motion, this is the direction that it would tend to accelerate. It would change its velocity along these lines. So if you have, and this is what makes electricity a little bit difficult for us, because we have to accommodate electric field lines that go inward like that, and electric field lines for a positively charged sphere that go outward, right? And now, here's another thing I want you to make a note of. And this This is kind of a mental IQ test, but go ahead and write down my question. It's not on a clicker question, but I want you to think about it. This positive test charge, marked in red, you set it at rest at that position, it will go inwards towards the negatively charged sphere, all right? Now, if that's true, where is the potential energy highest? Far away from the negative sphere or close to the negative sphere? It tends to move and accelerate toward the metal sphere. So where is potential energy higher? A higher value of potential energy for this. What do you think? Raise your hand if you have an idea. What do you think? Why do you say that?
Because if it accelerates on the way in, then your potential energy is greater when it starts.
Good. It's accelerating on the way in, so it means it's getting more speed as it gets closer. So it's a little bit like gravitation. All right? And in fact, there's a lot of similarities. The electromagnetic interaction is very similar to gravity. Right? And we know that the high potential energy gravitationally is further out and smaller closer in. Same thing here, but only if you're talking about a positive test charge and a negative sphere. If you were talking about the positive sphere, it would be the exact opposite. And that's why potential energy is so difficult and tricky when you're talking about the electromagnetic field. Now, go ahead and make a summary side note. The field lines go inward to a negative charge, just like in this picture. The field lines go outward from a positive charge, like the Van de Graaff picture that we had just a minute ago. All right? Let me repeat that. Summary side note. Electric field lines go inward toward a negative charge, like we've got here. The field lines go outward, radially outward, from a positive charge, which we had on a previous slide. Now I'm going to show you something called an electric dipole. A dipole is a combination of a negative and a positive that are fairly close together. Now, don't try to make this sketch, but definitely look at this. Look at this diagram. I have a blue negative charge and a red positive charge, and they're fairly close to each other. Now, over here, around near the negative charge, you can see that the field lines are pointing inward. Over here, near the positive charge, you can see that the field lines are pointing straight out, radially outward. Okay? And that's what nature would do. But in the area in between, they gracefully merge so that these outward ones here by the red, okay, I'm down here at the southwest. See where my cursor is? The southwest quadrant of the positive charge. And this arrow's going southwest, but whoa, it starts easing over here, and eventually the arrows start pointing over here toward the negative. And that's what happens if you're in this area between the two charges. This is what the field lines look like. Go ahead and make this sketch. Okay? The field lines over by the negative charge over here on the left go inward. And over here by the positive charge on the right, they go outward. but they gracefully curve over, and they're left to right symmetric. Above and below symmetric. There's two symmetry lines here. There's a vertical symmetry line through the middle, and there's a horizontal symmetry line through the two charges. Okay? So that the field lines look identical, top and bottom, when you flip-flop. And they also look identical, the shape anyways, looks identical when you flip-flop left for right. Okay? Also, in your sketch, I don't know if you're getting it, and it's tricky, you know, so you might not be a second Leonardo da Vinci with this sketch, but the electric field lines right down the symmetry line here between the two charges is straight to the left. The arrows are always straight to the left, right in here. Now, if you go a little bit away from the symmetry line, they're not straight. You know, up here, above and to the right of the negative charge, the field lines are kind of pointing down to the southwest. Over here, down and to the right of the negative charge, the field lines, they're kind of tilting upward to the northwest. All right, but right down the pipe here, right down the middle, they're straight leftward. Also, right in here, go ahead and put like a little dotted line circle right in this central region, kind of about halfway across or halfway between both of the charges. Right in that central region, where my cursor is right now, the electric field lines are very, very uniform. They're very uniformly distributed, right? There's not a lot of distance between them. And my wonderful students, where the electric field lines are dense, they're closely spaced, the electric force is large, you know, whichever direction the electric force is. Right? So let me repeat that. Where the electric field lines are close together, mathematically and with a huge amount of calculus, that signifies that the force is great. Where the field lines are, see how they're kind of getting spread out here in the upper right and down here in the lower right. And at each of the corners, the four corners, the field lines are starting to get spread out. They're still there, but they're getting spread out. That signifies that the force is getting weaker. Right? The electric force is getting weaker. Now, I want to go through this with you again. We'll be talking about electric dipole field. It's the most basic field other than the straight out positive charge field or the negative, straight inward negative charge field. Electric dipole field is pretty important. By the way, did you ever see that experiment from like 5th grade science class where you take a bar magnet and you sprinkle iron filings on near them, and you can see the magnetic field lines? The magnetic field lines of a bar magnet are exactly the same shape. Exactly. And it is not a coincidence. Okay? Now, if you have a horseshoe magnet, it's not quite the same. But in between the two tips of a horseshoe magnet, yeah, it's very much like this region here. So electricity and magnetism, yeah, they're definitely, I mean, we could spend an entire semester talking about that. And that's not even talking about photons and the momentum and energy of the electromagnetic field. It's a lot to learn. Now, I want to reinforce some stuff we talked about last time, and that is about charges in matter. And electrons, of course, they're the small ones, and they move easily. The protons are bigger in terms of mass, but the protons have the same size. They're positive, and electrons are negative. So whatever the electron has, the proton has the same charge, but it's positive on the proton. Okay? They interact by an electric force that we're going to study here in just a few minutes. Like charges repel and unlike charges attract. Um, and you can think of that in terms of individual electrons and protons, or you could think of it in terms of ions. And an ion is an atom that's either lost or gained one or two or more electrons. All right, now, this is a lithium ion. Actually, the pink panel up here on the upper left, that's a neutral lithium atom. It's kind of, it's a diagram for it. Okay, 3 positives in the nucleus, that makes it lithium. And then 3 electrons on little kind of circular orbits around there. Kind of a schematic diagram. If you strip one of those electrons away, that outer one is the easiest because it's out there at highest potential energy. It's bound. The force out there is weaker, so it's the most easily stripped. It's called the valence electron. If you strip that one away, you have a positive ion. And the positive ion will act as a unit. So you can have charges or you can have ions interacting. Now, a negative ion is one, okay, now my pink panel down here represents the neutral lithium atom. And now I've added in the upper panel an extra electron up there. Okay, so there's 2 on the second orbit. And you can do that. You load up another electron in there. That electron will be bound. It's not very strongly bound, but you can load it up. And it'll become a negative ion. All right. Now, normally speaking, lithium is going to oscillate between a neutral and a positive ion. But you can force it to be a negative ion for a short amount of time. It'll do that. And then those 2 ions could attract, so you could have a positive lithium and a negative lithium ion, and they would form an ionic bond. And ionic bonds are pretty strong. It's a positive atom attracting a negative atom. Positive ion attracting a negative ion. And the most famous example of that, of course, which I mentioned last week, is table salt, NaCl. The sodium is positive. The chlorine stole 1 electron from the sodium and became a negative ion. And so you got positive attracting negative ions. They form an ionic bond. We'll talk more about that later this week. We also talked about electrical conductors and what it means. Basically, it means that in the substance that you've got, there are some electrons that are easily moved around from point A to point B. All right? So, for example, metals are usually fairly good. Gold is really good. Copper is really good. Iron is okay. It's not, the best, but it'll conduct electrical current. Graphite is actually pretty good. They have carbon they can just make electrodes out of carbon. An ionic solution like the acid inside this lemon. This is a lemon battery, 2 different kinds of metal, a piece of copper wire, and a steel paper clip connected to another wire. When they're connected, ions will flow, electrons will flow, and you'll get current through the wire, and that little compass needle off to the right will deflect left or right depending on the direction of the current. Now, another, and this particular experiment is one that I recommend to all you secondary and elementary ed teachers that you can easily do, and we sometimes do it in lecture as well. Electrical insulators are the opposite. The electron motions, the electrons are bound to the nuclei a little bit more strongly, or bound to the molecule a little bit more strongly. So yeah, they, theoretically they can move, but it's not that easy, right? And if that's the case, you have an insulator. So the added charges, it's not like a metal sphere where the charges easily redistribute themselves to the lowest energy state. In an insulator, the charges, they would like to push apart from each other. They'd like to repel, but it's hard going. So if you deposit some extra charge on there, it doesn't tend to make a current. That makes it an insulator, for which examples are glass, wood, and diamond, stuff like that, ceramic. And then the third in-between category is the semiconductor, which we make out of silicon and arsenic and gallium and stuff. And it depends on whether a voltage is applied to the piece of silicon, whether it conducts or resists. It becomes an insulator or a conductor. And those are called semiconductors. And that's basically how the little ones and zeros migrate through your cell phone and onto the display screen, or through your cell phone and out to the speaker that you're listening to. Okay, they transformed into work at the speaker. So we talked about this last time. I'd like to talk about now some new material about Charles Coulomb. This is the French scientist who figured out the basic distance dependence of the electromagnetic interaction. We now call it the Coulomb interaction because of that. Now, he was from Martinique. He was a military engineer. In 1776, the year of our independence here in the United States, the US of A, he moved over to Paris, France, and he became an academic scientist. So, they go to France, Paris, start eating cheese, stuff like that. But what he was pretty smart. He was a military engineer, so he knew how to build things and design things. And what he did was develop a balance for measuring very, very small forces. It's called a torsion balance. It stayed horizontal. So a regular balance, it tips left or tips right, depending on what you're trying to balance. But this one, it would stay horizontal, but it would swing. And every degree of swing or twist, torsion, we call it, corresponded to a certain number of newtons. In other words, you could get a torque, on the end of your balance, a little bit of force forward over here and a little bit of force backwards over here on the other side, and you'll get something to spin, to twist, right? Some torque. Change the angular momentum state. And the more twist, the degree of twist, Kimmy, allows you to see how many newtons of force are being developed. So he used that to figure out the very, very tiny electrical forces on charged objects. Now, in his day, they had to charge stuff up by rubbing. All right? And there's ways to measure that and so forth. But and they had various machines to charge things. But he was able to do that and measure the number of newtons between two charges. And what he found was that there was an interaction very similar to universal gravitation. It was a force between pairs of charges, so a pairwise interaction. And that the size of the charge was one of the two primary factors. Also, the distance apart was the other primary factor. And the formula that he developed or that he discovered was, whoa, Mother Nature uses a force law very similar here to what the gravitational force is. Remember, Newton's law of universal gravitation, G times m1 times m2 over r squared. This one is little k times q1 times q2 divided by r squared. So q is the size of the charge, r is the separation distance, and here's the diagram up here. And the forces of interaction are mutual. They mutually interact, and they can attract and I've got a red Q1, that's positive, and a blue Q2, that's negatory. All right, so they'll attract. They'll have mutually interacting forces, mutually attracting. Right, but unlike gravitation, it is possible to have repulsion. So there's two kinds of electric charge, and if you have positive to positive, they'll repel. If you have negative to negative, they'll repel. That's not what happens with gravitation. In addition, charge is not measured in kilograms. It's measured in coulombs. And that unit of measurement for electric charge, basically how much static a charge has built up, that is named after Professor Coulomb from Paris. Now, I want to show you how this law accommodates repulsion. So what we're going to do is look at this force law. Oh, by the way, the letter K is a conversion constant, just like capital G, Newton's gravitational constant. The letter K is known as the Coulomb constant. And if you want to write it down, it's inside your textbook. It's 9 times 10 to the 9th Newtons meters squared per Coulomb squared. We're not going to calculate with it, but it is a number. It converts the product of two charges, Coulomb squared, divided by the square of a distance, meters squared, and it converts it into newtons. So that's what K is. Now let's say that we've got this force, Q1 and Q2, acting between an electron and a proton. So I put a -1 and a +1 here. Okay, so Q2 is a proton, and Q1 is an electron, so negatory. So -1 and +1. And let's say that force, whatever it is, it's going to be negative in this scenario. So it's going to be a leftward force. All right. So the force on the electron is over here on the right, and it's getting a leftward pull. All right. Now, if I switch out and in place of the electron I put another proton, here's a +1 combination. If I put instead of my electron over here on the right getting pulled to the left by a so there's a proton over here. McGuire, raise your hand. Okay, Robert, right? Robert over there is where there's a proton. That's the one in square brackets. Right over here is an electron, negative, and it would get pulled towards Robert. Now, if instead of an electron here, I put a proton, that's the second or the third line down in my equation block. Okay, that's +1. So K times +1 times another +1. That means that the sign of my force now changes to positive. So in our accounting, that would mean it's to the right. And if Robert's got a proton over there, and I've got a proton here, this proton here that I'm studying is going to get pushed off to the right. Right? And that's reflected in the +10 here. Right? So we haven't really specified the distance or the size of the charge, just that it's negative, and that we got plus and minus 10s. Right? So there's the switcheroo. Okay, so Robert's got a proton. I've got either an electron or a proton. If I've got an electron, I get 10 newtons towards Robert. If I have a proton, I get 10 newtons away from Robert. All right, so that's reflected in the plus or minus signs. All right, so here are the two different interactions that we model. So if you just go electron and proton or proton and proton, you can see how the forces change. And here's a little side note on the conversion factor K. Now, I've got some clicker questions coming up, a few more. Make sure your clicker's handy. But let me pause for questions about this concept of left changing to right, attract and repel. Okay, let's keep going. Let's take a look. Go ahead and make a sketch of this. All right, now in my system, blue always denotes the negative if I'm on the computer. On a test, you'll just have to read what the diagram, because tests have to be black and white. But on the computer, blue is negative, red is positive. Proton charge is E, electron charge is minus E. So, I had a chemistry teacher when I was in high school, Dr. Cooper, and he always said, always make your electrons blue. So that's what I do. All right. Now, here's a question for you. We've got 3 sets. The top set up here, electron versus electron. The middle set, proton versus electron. And the bottom set, proton versus proton. Okay, do you have your sketch? Answer this question. Which pair has or have repulsive interaction? "15 seconds to vote. Ten, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. Okay. Go ahead and show this. All right. Most of you voted for D, and I'm glad nobody voted for E. Okay, switch back over. It looks like some of you voted for B, and B is exactly wrong. B is the only one that doesn't have a repulsive attraction. So top and bottom are actually true, but middle pair is definitely not true. All right, let's do another question. Now this one I want you to think about carefully. What's the direction of the net electric force on the rightmost proton? Okay, so that's this one over here. It has 2 neighbors. Nearest neighbor is a proton. And the next neighbor out. And we'll assume that they're equally spaced. Nearest neighbor, proton, next neighbor out is an electron. So now this would make a good code question. Forming a sentence. All right, 10 seconds to vote. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. Okay, go ahead and show this one. Now, there's a little bit of controversy here. A bunch of you chose B for leftward, and that is incorrect. Please switch. The correct answer is rightward. Now, here's the way that you... Did you get it? You didn't get it? I heard you go like this. I mean, I saw you go like... I didn't hear you. I saw you go like this. Okay, anyways, here's how you want to... If you voted for leftward, here's the way you want to think about it. All right? It's pairwise interaction. So the rightmost proton interacts with a proton in the middle, okay, and that gives you a big force to the right. It also interacts, the rightmost proton, with the electron. Now the electron is going to pull it to the left, but the electron's further away. So R squared is bigger. Denominator big means quotient small. So it's going to have a smaller leftward force from the electron. Right? So make a note of that. Statement 1, rightward pull from the middle, or rightward push from the middle proton is big. Leftward pull from the electron is smaller because it's further away. Now, the reason that this is an interesting puzzle to work on, these, working out the relative forces, is because nature arranges itself into these kind of shapes. This is the retinal molecule. You see that little red out there? That little red atom, well, it's kind of hard to see. Right out here, I'll direct your eyes to it. This is supposed to be red. Gosh, it's not very red. Anyways, the retinal molecule is the molecule in the retina of your eye that, when it interacts with a photon of the right color, so somewhere between red, orange, yellow, green, blue, indigo, or violet, the visible range, that photon will make this molecule bend and unbend. So the relative forces between these atoms and the electrons that are orbiting the atoms is pretty important. Now, I want to talk about, for the last few minutes, the periodic table. And so we're dipping up to chapter 10. Your homework tonight is going to be to read in chapter 9 and chapter 10. And try to, just read and learn. Okay, the periodic table of elements. It was originally based on the properties of the elements. In other words, Mendeleev thought that if you correlate the atomic weight, which they began to figure out how to do that in the 1800s, and correlate that to the properties, like density or melting point or something like that, he found that if you did that, you would get repeating periodic behaviors if you arrange them in a table. Now, and so Dr. Mendeleev, the famous Russian from Siberia, is the one that figured out. And here's what his first periodic table looked like. And this is rotated 90 degrees from the way that we look at it today. But they didn't know anything about protons or electrons or neutrons. He was well before the days of J.J. Thomson and those guys. But he was able to figure out that, stuff like beryllium and magnesium were very similar. And up here, titanium and zircon up here, this row, and this column here formed an increasing range or a decreasing range in different properties, like radius or density or melting point or something like that. He saw that there were gaps. See, there's a gap over here between mercury and gold. Au is this chemical symbol for gold, all right? And here's bismuth over here. Now, these were the atomic weights that he was working with. They basically figured that out by measuring large quantities that will react or have reacted and seeing what the ratio of the masses are. And they could figure out, everything relative to carbon or everything relative to hydrogen or water, whatnot. And so the interesting thing about Mendeleev was he thought, okay, he didn't know about atomic weights or anything, but he postulated that in these gaps, they would find elements of nature, and he predicted what kind of properties they would have because they were in a gap in a certain one of these columns, and he was able to predict that, and by God, they found them not too long after he made his prediction. Now, the modern periodic table doesn't go by atomic weight, it goes by atomic number. Right? So what that looks like is this. Now here's the upper left corner of the periodic table. Atomic numbers up here, hydrogen 1, here's lithium. And basically that tells you, as I've mentioned before, how many items are in the nucleus. Or excuse me, how many protons are in the nucleus. And then down here, this is the atomic weight. So this is the stuff that Mendeleev was looking at. He was looking at atomic weight, and it didn't quite, I mean, he could see gaps and stuff, but it really becomes clear when you learn about protons and neutrons, and you can figure out an atomic number, the number of protons in the nucleus. That's the key. That's what makes it really periodic. So what we're going to talk about next time is we're going to start looking at this baby. Like here's copper, silver, gold, and Rg. I can't remember what that is. It's Röntgenium. And we're going to get these things sorted out here, layer by. See, here's the set: copper, silver, and gold. For Mendeleev, they weren't quite aligned. Now, in the modern periodic table, they're aligned in a stack. He had them aligned sideways, horizontally. That's all right. We could do our periodic table sideways if we wanted to. But he was working with atomic weights, not atomic numbers. So he had a little bit of scatter in his plot. But by God, he figured it all out. Now, we'll start with gold next time. You're dismissed. Your homework is to read chapter 9 and 10. And I'll see you. No homework other than that. Let's get my cursor.